Hello, students in this modern world. Right now, as you watch this video, approximately 5 billion lines of code are running simultaneously across the world. Your phone, the servers hosting this video, the satellites tracking GPS, the algorithms deciding what you see on social media, the systems running hospitals, banks, traffic lights, and nuclear power plants. All of it, every single bit, runs on concepts that were figured out between the 1930s and the 1990s by a surprisingly small number of people working on machines that were slower than your microwave. Computer science is not about memorizing code. It's about understanding how machines think, how information is represented, stored, organized, and processed. And once you understand that, everything else makes sense. I'm going to teach you the entire computer science degree in 25 minutes, binary to artificial intelligence, no coding background required. Let's start at the very beginning. The language of machines. Chapter 1, Binary and how computers work. Every computer in existence speaks exactly one language. Binary is a number system with only two digits, 0 and 1. That's it. Number 2, number 3s, no letters, just 0 and 1. Why? Because computers are built from billions of tiny switches, transistors that are either off or on, 0 or 1, no current or current, false or true. Everything your computer does, displaying this video, playing music, sending a message, is ultimately billions of these switches flipping on and off incredibly fast. Here's how binary represents numbers. In our normal decimal system, we count in powers of 10, ones column, tens column, hundreds column. In binary, we count in powers of 2, ones column, twos column, fours column, eights column. So the binary number 1010 means 1804S1201s. 8 plus 2 equals 10. 10 in binary equal to 10 in decimal. And text, each letter is assigned a number. This system is called ASCII, later expanded to Unicode. The letter A is 65. In binary, 100001. Your computer isn't reading letters, it's reading numbers that represent letters. Every image is a grid of pixels. Each pixel is 3 numbers, red, green, blue values from 0 to 255, all stored in binary. Every song is a series of amplitude measurements thousands of times per second, all binary. The entire digital world, every photo, every song, every movie, every website, every AI, is ultimately just enormous quantities of zeros and ones, interpreted at lightning speed. That's the foundation. Everything else we cover builds on top of this. Chapter 2, Data Structures. If binary is the language, data structures are the way that language is organized. How do you store and arrange information so it can be accessed efficiently? Different problems need different organizational systems. This is why data structures matter. Array is the simplest structure, a list of items stored in order side by side in memory. Item 1, item 2, item 3. Accessing any item by its position is instant. But inserting an item in the middle, you have to shift everything over, slow for big arrays. Linked lists, instead of storing items side by side, each item stores its value and a pointer to where the next item is in memory, like a treasure hunt. Each clue tells you where the next one is. Inserting anywhere is fast, just change the pointers. But finding item number 500, you have to follow the chain from item 1. Slow to search. Stacks. Last in, first out, like a stack of plates. You add to the top, you remove from the top. The most recent thing added is the first thing removed. Your browser's back button uses a stack. Every page you visit gets pushed on. Press back, pop the most recent one off. Queues. First in, first out, like a line at a coffee shop. First person in line gets served first. Print queues, task schedulers, queue structure. Trees, hierarchical structures. one root node at the top branching down. Your computer's file system is a tree, folders containing files. Binary search trees allow incredibly fast searching. At each node, everything to the left is smaller, everything to the right is larger. Search 1 million items in just 20 comparisons. Hash tables, the secret weapon of computer science. You put in a key, a mathematical function called a hash function converts it to a location, and your value is stored there. Looking up any key takes the same amount of time regardless of how much data you have. Instant. This is how Python dictionaries work, how database indexes work, how your password is stored. Graphs, nodes connected by edges. No hierarchy, any node can connect to any other. Social networks are graphs, you and your connections. Google Maps is a graph. Intersections are nodes, roads are edges. The algorithm finding your fastest route is traversing a graph. Choosing the wrong data structure for a problem is like using a hammer to screw in a bolt. It might work eventually, but the right tool changes everything. Chapter 3: Algorithms. An algorithm is a step-by-step set of instructions for solving a problem. Every program ever written is just algorithms operating on data structures. The most fundamental question about any algorithm: how does it scale? If the input doubles in size, does the time to solve the problem double, quadruple, stay the same? This is measured with big O notation, and it's one of the most important concepts in all of C's. O1. Constant time. Doesn't matter how big the input is. The operation takes the same time. Looking up a value in a hash table, accessing an array element by index. Perfect. O log n logarithmic. Time grows very slowly as input grows. Binary search, find a name in a phone book by opening to the middle, eliminating half repeat. 1 billion items, only 30 comparisons. Extremely fast. O n. Linear. Time grows proportionally with input. Search through an unsorted list from start to finish. Double the list. Double the time. Acceptable. O n superscript 2. Quadratic. Time grows with the square of input. Nested loops for every item. Check every other item. 1000 items is equal to 1 million operations. Get slow fast. Sorting algorithms, a classic CS problem that reveals deep truths about algorithmic thinking. Bubble sort, compare adjacent items, swap if out of order, repeat until sorted. Simple to understand. O n ao quadrado, terrible for large data sets. Nobody uses this in production, it's just taught because it's easy to understand. Merge sort, divide the list in half, sort each half, merge them back together. Recursive, O n log n, fast, stable. Actually used in real systems. Quicksort, pick a pivot element, put everything smaller to the left, everything larger to the right. Repeat recursively. Average O n log n, often fastest in practice, used in most standard library sort functions. Recursion. One of the most mind-bending concepts in CS, a function that calls itself. To solve a big problem, break it into a smaller version of the same problem until you hit a base case simple enough to solve directly. Merge sort is recursive, your file system traversal is recursive, fractals are recursive. Much of functional programming is recursive. Once you understand recursion, a whole class of problems becomes suddenly obvious. Chapter 4: Operating Systems. You have hardware, processor, memory, storage, screen, and you have applications, Chrome, Spotify, your camera app. Between them sits the operating system, the boss, the manager, the thing that makes it all work together. Diagram: hardware, OS, applications, you, Windows, macOS, Linux, iOS, Android. These are all operating systems. The OS has 4 main jobs. Process management. Your computer runs dozens of applications simultaneously, but most computers have a limited number of processor cores. The OS scheduler decides which process gets CPU time, for how long, and when to switch. It switches so fast, thousands of times per second, that everything feels simultaneous. It's an incredibly fast juggling act. Memory management. RAM random access memory is fast but limited. The OS decides which data lives in RAM and which gets temporarily moved to storage. It gives each program the illusion of having the entire memory to itself through a system called virtual memory. Programs don't know about each other's memory. The batch where you are to manual, the truck also had to summarize. File system management. The OS organizes storage into files and folders. It tracks where every byte of every file is located on disk. It handles reading and writing without two programs corrupting each other's data simultaneously. Common file systems, NTFS on Windows, apps on Mac, Extension 4 on Linux. Device management. Your OS communicates with hardware, keyboard, mouse, screen, printer, through software called drivers. A driver translates between generic OS commands and the specific language of each piece of hardware. This is why installing a new printer sometimes requires downloading a driver. The kernel is the core of the OS, the part that runs with maximum hardware privileges. It's always in memory, always running. Everything else requires services from the kernel. Security starts here. If the kernel is compromised, everything is compromised. Chapter 5: Computer Networks and the Internet. How does a message travel from your phone in one country to a server on the other side of the world and back in 50 milliseconds? The internet is not a cloud. It's a physical network of cables, routers, and servers spanning the entire planet. Undersea fiber optic cables carry the majority of international internet traffic. Data travels as pulses of light at nearly the speed of light. Data on the internet doesn't travel as one big stream. It's broken into small chunks called packets. Each packet travels independently through the network, possibly taking different routes in, and reassembles at the destination. This is called packet switching, and it's why the internet is robust. No single failure point can stop the whole thing. Key protocols, the rules that make it work. TCP over IP Transmission Control Protocol, Furo Internet Protocol. IP gives every device an address, like a postal address. TCP ensures packets arrive completely, and in order it checks for missing packets and requests retransmission. Together, they're the foundation of almost everything on the internet. DNS, Domain Name System. You type google.com, but computers use IP addresses, not names. DNS is the phone book that translates google.com to its IP address. Without DNS, you'd need to memorize strings of numbers to visit any website. HTTP Volatish, HTTPS, Hypertext Transfer Protocol. The protocol for web browsing. Your browser sends an HTTP request, give me this web page. The server sends back HTML, CSS, and JavaScript. Your browser renders it. HTTPS adds encryption, TLS, so your data can't be read in transit. How Wi-Fi works. Your router sends and receives radio waves. Your device has a wireless adapter that communicates on the same frequency. The router connects to your ISP internet service provider, which connects to the broader internet infrastructure. Every time you load a web page, here's what actually happens. DNS lookup converts the domain name to an IP. Your browser opens a TCP connection to that server, sends an HTTP request, server processes it, sends back files. Your browser passes HTML, downloads CSS and JavaScript, renders the page. All of this in under a second. Animated timeline, you press enter, DNS, TCP, HTTP, render, page loads. The internet is arguably the most complex engineering achievement in human history. And it runs on protocols invented in the 1970s and 80s that have just been incrementally improved ever since. Chapter 6: Databases and AI. Databases: How data is stored at scale. Every application that stores data uses a database. Your Instagram photos, your bank balance, your medical records, your Spotify listening history. The dominant type for decades: relational databases. Data organized in tables, rows, and columns like a spreadsheet. Tables relate to each other through shared keys. The language for querying them: SQL, structured query language. Select name, email from users where country is equal to US. That query retrieves names and emails of all US users. SQL is readable, powerful, and 50 years old, and still runs most of the world's data infrastructure. Indexes make queries fast. Without an index, finding one user in 100 million requires checking all 100 million rows. With an index, a sorted reference structure, it's nearly instant. Same principle as a book's index. NoSQL databases emerge for different needs: unstructured data, massive scale, flexible schemas. MongoDB stores documents. Redis stores key-value pairs in memory at extreme speed. Cassandra handles enormous distributed datasets. Different tools for different problems. ARM is Infotable Dalal of the one Mubatham. Modern applications have layers. Front end: what you see. HTML structures content. CSS styles it. JavaScript makes it interactive. React, Vue, Angular are frameworks that make building complex UIs manageable. Backend: the server-side logic. Receives requests, processes them, queries databases, sends responses. Python, JavaScript, Java, Go are common backend languages. API: Application Programming Interface, the contract between front-end and back-end. The front-end sends a request to a specific endpoint. The back-end processes it and returns data, usually as JSON. APIs are also how different services talk to each other. When you sign in with Google, that's an API call. Diagram: user, front-end, API, back-end, database, back. Version control: Git. Every professional developer uses Git. It tracks every change to code over time. You can see who changed what and when. Roll back to any previous version. Multiple developers work on the same code base simultaneously without overwriting each other. GitHub hosts Git repositories. It's where almost all the world's open source code lives. Chapter 7: Artificial Intelligence and Machine Learning. AI is not robots with feelings. AI is math that finds patterns in data. Traditional programming: a human writes explicit rules. If the email contains Nigerian prince and wire transfer, then mark as spam. The programmer anticipates every scenario. Machine learning: instead of writing rules, you feed the system thousands of examples and let it figure out the rules itself. How ML actually works? Simplified. You have training data, thousands or millions of labeled examples. Spam emails labeled spam. Cat photos labeled cat. The model starts with random parameters. It makes predictions, compares predictions to correct answers, calculates the error, adjusts parameters to reduce error, repeats millions of times. This process is called gradient descent, and the error calculation is called a loss function. After training, the model has learned statistical patterns, not rules a human wrote. It recognizes cats because it has seen 1 million cat photos and learned what features correlate with cat. Neural networks are modeled loosely on the brain. Layers of nodes, neurons. Input layer receives data. Hidden layers transform it. Output layer gives the result. Deep learning is equal to neural networks with many hidden layers. Neural network diagram with layers. Large language models, how ChatGPT and similar AI work. Trained on enormous amounts of text, the training task, given these words, predict the next word. Repeated billions of times across billions of documents. The model learns grammar, facts, reasoning patterns, coding, all from next word prediction. The result? A model that can write, reason, code, translate, and summarize. Because all of those tasks are ultimately sophisticated versions of, given this context, what comes next. Look, there's cybersecurity, how hackers think. Security is adversarial. For every defense, someone is trying to break it. Phishing, tricking users into revealing credentials through fake emails or websites. The most common attack vector, the fix, human training, and two-factor authentication. SQL injection, inserting malicious SQL code into an input field. If a website builds database queries from user input without sanitizing it, an attacker can manipulate the query to dump the entire database. Encryption, converting data into unreadable form without the decryption key. HTTPS encrypts your web traffic. AES encrypts stored data. RSA enables secure key exchange. Modern encryption is essentially unbreakable if implemented correctly. The CIA triad, the core framework of cybersecurity. Confidentiality, data only accessible to authorized parties. Integrity, data not tampered with. Availability, systems accessible when needed. Every security decision maps to one of these three. And that is the entire computer science degree. Binary, the language of machines. Data structures, how information is organized. Algorithms, the step-by-step rules that run everything. Operating systems, the manager between hardware and software. Networks, how data travels across the planet. Databases, how information is stored at scale. AI math, finding patterns in data. Cybersecurity, the arms race that never ends. You now understand the conceptual foundation of the technology that runs the modern world, not just how to use it, how it actually works. Next video, the entire MBA. Strategy, finance, marketing, operations, leadership. The stuff business schools charge $150,000 to teach. In 20 minutes, free. Subscribe. New degree every week. Zero debt required.